Welcome, my name is Erwin de Jong and today I'm going to give you this presentation on soil improvement and deep excavations. Not live, unfortunately, but live enough I think. Later on we will be discussing questions if you have any. You can use chat just to give any feedback that you would like. Normally if you would have been here, I would have asked you if any of you don't speak Dutch. In that case I could proceed in Dutch, but it's never been the case in the past 4 years, so I think it's not the case today, so it will be in English, and hopefully I will manage as good as you will. What you can see here in this first picture is, well, always the topic that I want to start with. On the right hand side you will see the model that you will be using if you're making designs, and as you can see the model is more or less the same as the picture on the left. The picture on the left is the actual excavation that we made at Tata Steel in IJmuiden, and the main difference is that on the left picture you can see actual people standing there, so you get a better grip, a better feel for the dimensions of this excavation. And safety wise, it's almost impossible to get the same impression of the excavation if you look at your model on the right. So don't underestimate the calculations that you're making and the impact that any faults in the calculations can have if you have the actual situation. Well, to start with a bit more introduction of myself. I started my career in 1988 with Fibro, which is probably familiar with you. In 2001 I moved to a contractor, Volker Wessels, the second largest contractor in the Netherlands. And the main aim was not only designing things and make calculations, but also doing the actual work. So Volker Wessels is a contractor with a specialized foundation construction company, VSF, Volker Staal en Funderingen. And they still exist today and they make some very interesting projects using all kinds of foundation techniques. And since 2011 I started my own company, GEOBEST. And as you can see we're now with 10 to 12 people in this firm, in this consultancy group. One of the main things that more or less makes us a bit different than other companies is that most of our employees have worked with contractors and with design firms, consultancy firms. So we actually know that there is always a gap between the consultant and the contractor, and our aim is to limit that gap, and we hope to eliminate the gap totally. That's always something of a challenge. What we're going to talk about today, soil improvement and deep excavations. The learning objectives are very clear, I think. We are going to learn which kind of soil improvements we can use at what type of soil. And basically to understand these improvement techniques, their use and their limitations. So soil improvement, why should we bother? Basically, the natural soil conditions are not always suitable for the things that we want to do. Primarily we encounter sand, clay and peat in the Netherlands. If we dig 200 kilometers or so, we will also encounter rock, but that's very deep. And soil improvement, our main aim is to reduce risk, to reduce building costs, and make in some way use of the natural soil conditions without having to install large sheet piling or diaphragm walls. Simply improve the soil so that it's more suitable for the things that we want to do with it. This table shows you an overview of all the soil improvement techniques that we have, that we're familiar with, and well, the ones in red, well, we're going to discuss more or less all of them. Not all of them in the same, will have the same attention, but we will cover, well, fairly all of it. So if you look at the soil improvement techniques without admixtures, then you can do those in non-cohesive soils or fill materials. And basically what we're going to do is we're going to add energy. And by using energy, we are going to compact the natural soil. Well, that's the first part that we're going to discuss. So if we take a further look at compaction methods, well, I'm going to talk to you today primarily about rapid impact compaction and Fibro Compaction. And since compaction is all about energy and primarily not using any admixtures, well, of course the result will be very dependable on the original soils. The main goal of compaction is to increase the strength and stiffness of the soil, to reduce any possibilities of liquefaction. Primarily that is done in well, areas where you have a lot of earthquake problems, and if we're using it primarily on non-cohesive soils, we're talking about fills. All over the world, Dutch contractors are building new land, doing land reclamations, and we have to compact all those soils that are made by Boskalis and Van Oort. Then again, if we have existing soils after dredging or simply existing soils and we want to compact those, we always have to check whether those soils are suitable for compaction. One of the first items that we have to look for is the density, the original pore volume of the non-cohesive soils that are present. Well, primarily we're talking about a loose packing if we have a pore volume between 40 and 50%, a dense packing if the pore volume is between 25 and 30%. The range of the pore volume primarily is determined by the grain size distribution and the shape of the grains themselves. Compaction, by simply adding energy, is always time consuming because, well, we don't know how much energy we have to use to get the result that is required. Then again, water is present most of the time in the soils, and water will limit the possibilities to compact those soils. If we have very permeable soils, then we'll have a rapid compaction because the water can easily flow out. If we have a low permeability, then there will be a slow compaction. If you use a lot of energy and you have a low permeability, you will quickly create quicksand instead of reaching compaction. The influence of groundwater. Well, we could compact non-cohesive soils below the groundwater table, but then we would use a very special kind of technique because it actually creates a lot of problems if the soil is that wet and that there's no possibility for water to disperse, then it will be very difficult to compact the soils. So normally if we do if we try to assess whether the soil is compactable, we start by examining the permeability and the void ratio. And of course, if the particles are very small and we have a lot of fines, then it's almost impossible to compact those soils, because although it's a non-cohesive material, it more or less resembles clay. and clay is a cohesive material, and then you will have very large problems if you try to compact clay with a lot of energy. So one of the main techniques that is used nowadays is the rapid impact compaction technique, REC or also CDC. REC is the name that Boskalis use, COFRA. And if you check the YouTube link below, then you will see the actual work in progress. Basically, it's a large driving hammer and a steel plate. And simply by moving the steel plate and giving a lot of blows will compact the soil beneath. You can do that in a pattern, and of course the pattern that you're going to use largely depends on the actual soil conditions that you're starting with. It's very hard to make any kind of design calculations, so basically what we're doing is simply trial and error. So we're going to give a fixed number of blows, and we do that, well, at a certain space, and then afterwards we're going to check by means of CPTs what the result of our compaction is. Then we can adjust the pattern, we can adjust the amount of blows, and then we'll have the required result. There are a lot of publications on this method, and it shows you that, well, you could reach a depth of up to 7 meters, depending on soil conditions and depending on the amount of energy that you can use at the site. A very interesting example is the Sea-Lock IJmuiden, where this technique was used to compact the temporary building pits. As you may know, that the sluice lock heads on both sides were made by installing large concrete caissons, but they had to be built before that. They were built in a building pit, and this building pit was filled with sand, and that sand had to be compacted. So here you can see the execution, the construction of the building pits by sheet piles, an overview of the total area, and here you can see the C2C, the rapid impact compaction, the equipment that was lowered into the building pit, and then they started hammering. What they forgot in this particular example is that they didn't install enough drainage beforehand. And the groundwater table was actually not that far below the surface level, and after a number of blows the water reached the surface, and well, they couldn't continue. So they had to install additional drainage, and then the work processed, and all went well. If there is a need for a larger depth than 5 to 7 meters, then we can use another technique, the technique of Fibro Compaction. Basically what we're doing, we're going to install a needle, a vibrating needle, till a fairly large depth, and that will result, the compaction will result in settlements, and by adding granular material we can further compact the soil. I've also got an example for this one. This is the starting shaft of the bore tunnel in Rotterdam, and we first had to make a soil improvement by taking all the Holocene clay and peat layers out, replacing them with sand, and then compact that sand to reach the required density. So if you compare this picture with the previous picture, then you can see at the sheet piles in the back that, well, we reached a settlement of the surface of about 2 meters. So we had to fill that up again and continue the compaction. These two CPTs, they show the results before and after, and well, the fixed lines and the dotted lines that you can see are the contract requirements, and you see that the actual compaction, well, you can say it was too good. We used too much energy, so the results were that we exceeded our expectations and we exceeded the client's requirements. It wasn't a problem, but well, we could have used less energy, we could have finished the job earlier, sooner, made more money, but it didn't happen. So if we look at the Fibro Compaction, the results, the compacted cylinder with this kind of technique is more or less 2 to 3 meters. So an acceptable center-to-center distance is 1 to 2.5 meters to have, well, enough overlap between the several locations. You could reach depth up to 20 meters if you would like to. Then you will reach the limits of, well, the regular equipment that we can use. And as you can see, you need to add a lot of sand just to maintain your surface level height. If we encounter material that we can't compact that easy, if we have too much fines, if we even have clay, then we should stop using this technique. In German, this technique is called Rütteldrückverfahren, and we should consider a technique that's called Rüttelstopverfahren. Also, well, you can also use it more or less to create better bearing capacity. And with Rüttelstopverfahren, you're not only compacting the soils, but you're also actually replacing cohesive soils with granular material that you can compact a lot easier. Okay, next we're going to talk about soil improvement techniques with grouting. And well, we consider chemical grouting, jet grouting, grouting in general are techniques that are used to, well, to improve soil conditions, whether the soil is sand, non-cohesive soils, or cohesive soils like clay and peat. So we're going to talk about jet grouting, permeation grouting with either cements or chemicals, and we're going to talk about soil fracturing. Basically in this slide you can see it all. With grouting techniques we're primarily filling any pores that are present in the soil, and we if there's air in the pores, if there's water in the pores, it doesn't matter, we're going to replace that with an injected anything. Basically this is only possible in non-cohesive soils, in granular soils where we have enough pores. The second technique is jet grouting. With jet grouting we're going to use a lot of energy, and if we want to, we can replace all the soil that is present and replace it with a cement slurry, cement bentonite slurry, whatever. It depends on how much stiffness we require and all the other elements that our soil improvement has to fulfill. And then there's also the technique of fracturing and compaction grouting. They resemble each other a bit. With fracturing, basically what we do is we first make the pores in the soil. So if there aren't any pores, you could always consider fracturing first and then filling all the fractures and the fissures that we make, filling them with a cement binder. Compaction grouting, our primarily use is simply to compact the soil by introducing another material. And under high pressure, we're not aiming to make any kind of columns, we're not aiming to make fractures, we're simply aiming on improving the density of the soil. Well, how to define grouting techniques? One of the ways is by making the difference between cement and chemical grouting. Cement or micro-cement, well, we can use cement in rock, we can use it in hard soils and gravels with big pores, and it will result in a large effect that will be there for, well, 100, 200 years. If we look at chemical injections, then we need finer pores. It's possible in sand and fine gravel. But it will not remain there forever. Chemical gels, they almost always, well, if you have a soft soil, then it will last for 2 to 5 years. If you make a hard gel, it will last longer, but it's not going to last for 100 years or more. If we use jet grouting, we're completely destroying the soil structure, and well, if we want to, we can extract all the soil and replace it with cement. Well, soil fracturing will fracture the soil is broken, and the fractures will be injected. Its main use, well, to reduce permeability, that's the most common use in the Netherlands nowadays. We can make horizontal layers in building pits, and well, they will have a reduced permeability, and they may be even non-permeable. Well, there's a lot of discussion about that. Not every project is as successful as we would want it to be. Another purpose is to increase strength and stiffness. So if we use cement, then it's primarily in dams or retaining walls, and it will have a lasting effect. If we use chemical injections, we use it for temporary constructions in building pits or underpinning of foundations. When we're going to use soil fracturing, basically if, well, nothing else is possible because it's an expensive technique, you need a lot of pressure to create it, and the result is not always that predictable. So there's a lot of risk with this kind of technique in itself. And well, of course, we all know since the bored tunnels in Amsterdam that you can use compensation grouting to compensate any volume loss, for example, by the boring of the tunnel itself. If we take a further look at jet grouting, then the machine that we're using is not so big. The machine itself is more or less a normal grain that is also used for digging or removing soil, and it's a relatively small machine. It weighs up to 40 to 80 tons, and it's equipped with well, some kind of an auger that we can use to drill into the ground. But it's not all that we need. Of course, at the end of the drilling bit, there's the actual place where we do the jet grouting itself. And we use jet grouting with very high pressures, up to 500 bars. In this example, you even see 800 bars, so very high pressures. And we can use the one-phase, the two-phase, or even three-phase techniques. Basically, if you inject only grout, then it's a one-phase technique. If you use grout and air, it's a two-phase technique. If you use air, water and grout, then you have three-phases technique. Not always you need three phases. If you use three phases, you can make larger columns, you get higher stiffness, you get better results, but you not always need those perfect results. And of course, the one-phase systems is a lot simpler, and for some projects far more cost-effective. And it's not always better to make large columns. Sometimes you get a higher reliability if you make more small columns than if you make only a few big columns. This is a picture of an actual drilling bit for jet grouting. You can see the large, well, the wings on the side. Those are primarily used to make the hole, to get the drilling bit to the required depth. And the detail is of the nozzle. The nozzle is only a very small hole that the the water, air, or the grout itself is injected in the ground with very high pressures. As I said before, you don't only have that small machinery, unfortunately, you need a lot of extra equipment. You need a pump, because, well, you have to create those 500 bars. And you need a lot of hoses, simply not only to introduce the cement to your drilling hole, but also if you're removing a lot of soil, then you have to pump away that soil as well. So you have to make sure that you have enough space in the near vicinity of where you're doing the actual works, just to collect all the soil that you're removing. And the soil that you're going to remove, well, it will also contain some cement, so it will harden and you will have to dispose of it in some way or another. And of course you need a cement silo with a lot of bulk that you will have to use well, to create your columns. As I said, very high pressures. Normally you wouldn't see these kind of pictures below surface because you're going to use those high pressures in the soil, and that also makes clear that you can't make a column till surface level, because you will always need some extra soil on top simply to create safety for these high pressures. So if you're going to make columns, the columns will be constructed till 2 or 3 meters below surface level. But if you want to clean your equipment, of course, then you can do it above ground, but this is only water that's coming out. You can make retaining walls, and the beauty of this technique is that you can create these kind of walls below existing walls. And you can see here an extension that we did a couple of years ago at the Beelden at Zee Museum in Scheveningen. They wanted, a new cellar to put some things in, and of course by using the jet grout technique, and you can see here a jet grout wall that's made with anchors, it was possible to use the maximum of the available space, because we could put the jet grouting columns directly below the concrete wall, so we can optimize the space that we had. At the building pit level you can see the actual columns that are still left there, the top half that was excavated. Jet grout technique is also very suitable to if you encounter these kind of problems. This was a large duct that was present, and well, the large parts of the wall were made by using the soil mix technique that we're going to discuss later on. But of course the soil mix technique is done from ground level, and you can't pass these kind of ducts by using that technique. So we used jet grout columns to fill the gap between the CSM panels that we made, and in that way we could close this gap. You can use all kind of patterns if you want to make a retaining wall with jet grouting columns. As you can see on the top, there's a single row of columns, and of course if you want a higher reliability and you want to be certain that you have the required overlap and the required stiffness of your construction, and it could be better just to use a double row of columns, or even a third row if considered necessary. You could also use, well, there are techniques that you can make more or less flat panels, but of course then the risk that you do not have sufficient overlap, well, that increases a lot. So basically it's not something that's done regularly. Most of the time you will always see either a single row or a double row of columns. And well, objects that are already in the ground will give you a lot of problems, because well, you have something like shadowing. You can't make a jet grout column past an object that's already in the soil. So if you have a lot of wooden piles, as in this example, then the jet grout will simply stop in front of the wooden pile. Of course, if the wooden pile is very near to the jet grout drilling bit, then it could be the case that you simply remove also a wooden pile. But if it's a concrete pile, that's not going to happen. So everything that's already in the ground could be a problem if you want to create a jet grout wall. One of the other things, and that's primarily with all the techniques that we use into the soil, we always have to consider the lack of accuracy with increasing depth. We also always have an inclination of maybe 1.5% with depth. So if we have a neat pattern on the surface, then the pattern will be different at 20 meters depth. So if we consider how much the columns should overlap, then we should always consider this lack of accuracy. Of course, if we make larger columns and we reduce the center-to-center distance, then we're always sure that at 20 meters depth we still have an overlap. Well, some of the strengths that we can reach, of course, it always depends on the original soil, but if we remove all those soils, it simply is based on the amount of cement and that we're going to use filling the holes that we made. We know some examples from literature where we've tried to make a horizontal layer using jet grouting. And of course we have the famous project in The Hague, the Trent Tunnel, in which we tried this technique, but you can imagine that if you miss one of those columns and you forget to make one of those columns, then we'll have a large gap in your horizontal layer. And if it's never going to be fully watertight, and if you're not able to maintain a groundwater level on top of your surface, well, then you could be in big problems. So basically nowadays nobody's doing that anywhere in the world because, well, primarily of the Trent Tunnel. And if we take a further look at permeation grouting, well, the possibility of filling pores depends on the grain size distribution. That's on the one side, that's the natural soil conditions. On the other side, it's, well, basically determined by the viscosity of the injection fluid itself. If we have very small particles in our injection fluid, we can install it in soils with smaller pores. It's as simple as that. If you look at chemical solutions, well, we can always use them in sands, even sometimes in fine sands, but you can never use it in clay or peat. There simply is not enough pore volume in those materials. The main differences between grouting and jet grouting, you can see in this slide. It's basically the difference in the pressures that you're going to use, the flow rate of the material that you're going to inject, the diameters that you can reach. Well, with grouting we are only filling the space between the soil particles. With jet grouting we can destroy the soil structure completely. Well, by grouting, normally we're going to put holes in the soil first, injection points, then we're going to fill them, one after the other. If we're doing jet grouting, we're making complete columns in one phase. Yeah, but you consider also that if we do a chemical grouting, we're basically working with two components, and as soon as those components reach the soil, then a chemical process starts, and it will last about 45 minutes, and then you can't simply inject any more material because it will have reacted. And after it has reacted, it has its fixed position and its fixed size, and you can't expand any further. This shows you a grain size distribution from silty material to gravel, and as you can see, you should use a different kind of binder in a different kind of soil to get the best results. With chemical injection, the viscosity of the fluid that we're going to inject will always have an influence on the area that we're going to inject. And if the viscosity is more or less like water, you could make maybe holes up to, depending on the pressure that you're going to use, you could make holes of maybe even 10 meters. But the viscosity of, for example, waterglas is over 50 times the viscosity of water. And normally the bulbs that we can create using waterglas is more or less limited to 1 meter. If we look at chemical injections, there's an interesting article on the chemicals of injection fluids. I put it on the slide here for you to see. And well, normally the basic is a lot of water, and it's simply adding the water glass and another binder that's going to create, well, that the result, the end material, is going to be harder or more flexible. So if we have a fluid that is only meant to lessen the permeability of the soil, if we want to create a horizontal non-permeable layer, then we will only use 1.5% of harder. And if we want to create also a lot of stiffness, then we could use up to 5% harder. Dus that will be a total different injection fluid. As I said, we can always use cement, and then we do not take the normal cement that you will use to put bricks together, but ultra fine cement that will be possible to inject also in large pores. If you look at the process that we use to install these chemical fluids, then you always have to drill a hole first. And well, you can drill a hole and inject at the same time. You can drill a hole and leave injection points into the soil. And you can also use injection elements like a tube-machete. And the tube-machete has the primarily advantage that you can inject at certain points along the shaft, so you can create even a wall if you would like, or you can create several layers on top of each other. This example from the Vecht aqueduct in the A1 highway near Muiden. And you can see here the installing of a lot of these injection points. And every injection point, well, has a cable and it goes to the surface, and we're going to use those cables to inject them later. But those are a lot of injection points, and of course you shouldn't forget one if you start filling. If we use the tube-machetes, then we also make a drilling hole, but we put the tube-machete in, and afterwards we can use packers to inject well, at certain levels of the tube-machete. This is the Vecht aqueduct again, and you can see all the tubes coming from the injection points, and they all have to be labeled and they all have to be filled. And of course, if you have such a large area, then it's always possible that you simply miss one of those injection points, and then you could have a big problem because you will have a leak in your non-permeable floor. What we normally do with the horizontal layer, we use a center-to-center distance of approximately 1 meter, and well, that involves also that we may create spheres or bulbs with the same diameter. If you want to make a vertical wall or a sheet, then we use the tube-machetes with openings that are spaced well, more or less 33 centimeters. We make some kind of a bit smaller cylinders, and well, we can use as much cylinders as we would like. Dan hebben we hier een film.
GMP bodeminjectie is sinds 1998 actief op de markt van bodeminjectie en calamiteiteninjectiewerk in bouwputten. Binnen veel bouwprojecten worden tegenwoordig ondergrondse bouwlagen gemaakt. Eén ontwikkeling op het gebied van ondergronds bouwen is het realiseren van een waterremmende onderafsluiting van de bouwkuip door middel van bodeminjectie. Nadat de verticale grond- en waterkerende constructie is aangebracht, bijvoorbeeld door middel van een damwand, kan de onderafsluiting worden gerealiseerd. Eerst worden injectieslangen in een vooraf bepaald stramien, trillend of borend, op diepte gebracht. Vervolgens worden deze stuk voor stuk geïnjecteerd met een mengsel van water, glas en harder. Tijdens het injectieproces wordt het aanwezige grondwater verdrongen en vervangen door de gewenste injectievloeistof. De geïnjecteerde vloeistof reageert en zo ontstaat er een waterremmende laag. Eventuele palen of ankers voor de definitieve constructie kunnen vooraf worden aangebracht zonder de waterremmendheid aan te tasten. Na voldoende uitharding, circa 6 à 7 dagen, kan het water uit de poriën van het zand worden onttrokken. Na ontgraving zorgt de injectielaag en het bovenliggende grondpakket voor voldoende neerwaartse druk. Hiermee wordt opbarsten voorkomen. Enkele voordelen van horizontale onderafsluiting middels bodeminjectie zijn weinig tot geen grondwateronttrekking. Er kan droog en eventueel vanuit de kuip ontgraven worden, dus geen nat transport. Controle op waterremmendheid is voor ontgraving mogelijk. Hiermee worden risico's tot een minimum beperkt. B&P bodeminjectie biedt u een methode voor nu en in de toekomst.
So at the Vechtaqueduct, we thought we had it all under control, and we started making the first segment that you can see at the riverside, and it was dry. It was dry enough, but it didn't remain that way. So in the end, we had to fill the whole building pit again with water, and eventually we used an underwater concrete floor to build the aqueduct. So these kind of techniques, all soil improvement techniques, they're economical, they're challenging, they're interesting. But if something goes wrong, you could be in large problems. And the Vechtaqueduct was a very large project. The width of the building pit is 70 meters, and well, the total length is up to 1 kilometer. So you can imagine that if something goes wrong, and if the construction site is that large, well, maybe it's simply normal sense that it would go wrong at some place or another. And if you don't recognize that spot at the correct time, well, then you will have to change your whole building strategy and your whole building solution. And of course, that costs a lot of money. This is a detail of the tuba machettes. You can see here that it's in the soil, that there is an opening in the tuba machette where you can use some pressure to open the pores of the machette, and then you can introduce the chemical that you want to inject. You see here the actual tubes. You see that the tube itself is blue, and all the black spots, those are the machettes, so those are the openings that you can inject your fluid through. And the example on the right bottom is the construction of the embankments below the A15 motorway. We had to widen the gap in order to make a tunnel for the high-speed railway. And we introduced used a vertical chemical injection to make that excavation possible. This is an overview from the container with all the equipment to fill the turbomachettes. So those are the pressure pumps that they're working on. And this is the end result. You can see that the excavation is more or less fully vertical. And in order to keep the injection at its place, we had to use ground anchors as well, simply to improve the horizontal stability of the injection itself. And some more pictures of it. Then the slide that I already started with, you've seen some of it. There's an article on the injection that we did over there. So we will also present you with that article for your information. Then for soil fracturing and compaction grouting, you could use these kind of pressures in the soil also to lift structures that are already there. And well, there's not much use for that kind of technique, but if we start making large bore tunnels and we're creating a volume loss, then you could use these kind of techniques to compensate that. Normally, if we fracture soils, we do that horizontally. So we make a vertical cut and we make the fractures horizontal. Well, this is an example. It looks like some of the houses in Amsterdam, but the first trial that we did was actually at the Sophia Spoortunnel. And we used grouting in order to lift the piled foundations and to prevent any settlements of these foundations due to the volume loss of creating the tunnel. Okay, then we have all kind of mixing methods. Mixed in place or cutter soil mixing are techniques that we use nowadays, have been using over the past 10 to 15 years, also in the Netherlands, to create building pits using the natural soil conditions, using the natural non-cohesive layers, and to strengthen them with cement. In the Scandinavian countries, we're also using this technique simply to improve the soil stiffness. And then we're going to inject not only cement binders, but also lime cement columns, different kind of techniques to be used with different soils. If we look at the differences again between deep dry soil mixing and jet grouting, well, we use very low pressures with soil mixing. Bit similar to grouting techniques. The diameter that we are making is largely depending on the mixing tool that we're going to use. We will only have a limited amount of spoil because with deep dry soil mixing we're only going to add binder and mix the binder with the soil that's already there. So we're not removing all of the soil, we're using the soil that's already there. That also has a disadvantage, that if the soil isn't that well, we're not going to get those great results. And of course, the mixing tool itself, we need a lot of energy, but the strength and the stiffness of the mixing tool itself will limit the penetration possibilities in very stiff soils. If you have dense sands, then it's simply not possible to use these kind of mixing techniques. Well, in the last 50 years or so, there have been a lot of development, and those developments also, well, are visible in all kind of tools that we used. And it was simply a question of trial and error. What kind of mixing tool is giving a good result in what kind of soil? So I think they've tried it all by now. on the left-hand corner, you'll see the mixing tool that is primarily used in Scandinavian countries to improve the soil conditions of very weak soils. You can understand that if you want to drill this mixing tool to a depth of 10 or 50 meters, then it will give you a lot of problems because the stiffness of the mixing tool itself is very limited. If you look at the advantages of these kind of techniques, well, the equipment that you use could be rather small, and therefore you could use it at areas with very low bearing capacities because there's not a lot of pressure under the crawlers. It's cost effective. You're only adding binder and you're only taking out limited amounts of soil. So, well, you only have to have limited transportation because you only need a small amount of binder to improve the soil conditions. If you look at the drawbacks, well, you need some kind of water in the soil, water content, to create a good mixing, because basically you're adding either cement with air or cement slurry with water. But if the soil is completely dry, it will lose all its water almost instantly, and you won't be able to mix the soil in the way you would want to. Again, an example of the bore tunnels in Rotterdam. In the first part, closest to the starting point of the tunnel, we removed all the cohesive soils and replaced it with sand that we compacted. But further on, we improved the cohesive soils by adding cement. And this was done in 2004, so that's already 16 years ago. And the method itself wasn't that well known at that time. So we used a technique making a lot of columns, and in those columns we had been mixing the soil, the original soils, with cement. So if you consider the amount of cement that you're using, although it's far less than the amount of cement that you use in concrete, it still took an average of 250 kilograms of cement per cubic meter to get to the required depth and strength of 150 kPa. And another challenging demand from the client, the municipality of Rotterdam, was that they wanted a coverage of 100%. So all the soil should be treated from surface level till a depth of 20 meters. If you remember what I said earlier, if you want to have 100% coverage till 20 meters of depth, then you need to put the columns very close together at surface level. But, well, they used a mixing tool that you saw earlier, and it was not a very stiff mixing tool. So they simply couldn't put the columns closer to each other than, well, to have just sufficient overlap at surface level. So at one time they made some drillings to check whether all the soil was treated, and well, they found out that not all the soil was treated, and they had to make additional jet crowd columns to treat all the soil. I don't think it was necessary, but the requirements made it necessary. And if you do have some kind of mixing tool that is not very stiff itself, then there's always a possibility that you will lose a mixing tool. And in this project we did lose a mixing tool. It was at approximately 50 meters depth, and it was right in the direction of the bore tunnel. And if you're familiar with the fronts of the bore tunnels that we use in the Netherlands, then you know that we don't want any kind of obstacle in the way. Therefore, this mixing tool had to be recovered. So we made a large hole using this auger, and we drilled through all the mixed soil, and we did recover the mixing tool. As you can see on the right hand side, the actual soil that we treated there, it was primarily clay layers with some cement, and you can see that it looks more or less like a granule material once it's recovered. So it's actually quite firm, and you also see the teeth on the auger, and those were necessary just to get to the required depth. If we look at mixed in place nowadays, what kind of projects that we're doing with it, we're creating barriers, watertight barriers. For example, here near the river Rhine, as a leakage barrier. You need a normal amount of cement, again 300 kilos. We also use some bentonite, and we don't use bentonite to lessen the permeability. We primarily use bentonite to have the smearing qualities of the bentonite. So it's not done primarily for a lower permeability. It's more or less done just simply to make the augers go into the soil a lot more easy. The triple auger system by Bauer, if we're going to use that, we're also making panels. So 3 augers in a row, and by using this Pelgrim method, we're going to make a primary panel, another primary panel at some distance, and then we're going to mix in between and additional panels simply to create a perfect overlap. If you look at the further installation sequence of mixed in place, then at first we're simply going to install the augers or drill the augers to the required depth. Then we're going to homogenize the soil by simply removing the augers upwards and downwards and inject all the binder. And then we're going to finish the panel by extracting the augers. We have all kinds of sampling techniques to test the wall that were our final result. And this is, a partly excavated wall that we made at a trial field. The cutter soil mixing technique was more or less developed from by Bauer and Soletange, Bachy. It was a European project, so we more or less paid all. We paid for it ourselves, and it was made by Bauer and Soletange. And this kind of technique more or less resembles the diaphragm walls that we can use by making concrete, but with these we only mix the cement binder with the soil that's already present. So again, we first drill to the required depth, we dig to the required depth, then we're going to install the binder and move upwards again. So we have these 2 large wheels, and we can change the direction of the rotation of the wheels, and we do it differently when we're going down and differently when we're going up. These wheels, normally we have a width of the wall that we can make of 55 centimeters, but they have already been projects that they increased the width to 1.2 meters. And normally, if we have a fixed Kelly bar on top, then we can only reach a depth of about 20 meters. But if we change that system, we could go up to 60 meters of depth. If we have made the wall, in first instance, it's all liquid material. It's basically the binder, water, and the original soil. and if we want to or need to, we can install reinforcement. If we want to make a retaining wall, we will need that reinforcement. If we only need a non-permeable wall, we don't need the reinforcement. The last item that I'm going to talk to you about is freezing methods. Freezing methods are only used as a temporary construction. Of course, if you want to use a lot of money, you could freeze soil indefinitely, but that will be a great risk, because if you lose power or something, then you could lose your wall. And of course, basically it's done for temporary solutions. It's also a rather expensive method, so we're only using it if everything else fails. Basically, we make a difference between brine, which has a temperature of about -30 degrees Celsius. And if you want to freeze ground using brine, well, you have to take into account that it will take a certain amount of time before the ground freezes. If you're going to use liquid nitrogen, it's far more expensive, but since the material itself is a lot colder, the results will be visible a lot sooner. And it is only a question of days before the strength and the frozen ground is reached. As with all these techniques, primarily you have to make a hole first, simply to install the tubes that you can pump the material into. And you can see that you have different kinds of equipment regarding whether you use brine or nitrogen. Why should you use these techniques at all? Well, it's more reliable than grouting. Frozen soil, there's one thing that you know for sure, it's 100% watertight. If you have a leakage, however, and when it starts to flow, the water, then it's almost impossible to freeze it again. So you better not have any leakages to start with. The tubes that you're going to use are again within 0.5, 1.2 meters. You can either drill or vibrate those tubes into the soil. If you're going to use brine, then you have a system that you can pump it through, and you will have to refresh the brine constantly, because it's, as soon as you're going to inject it in the ground, it's going to heaten up. So you want to keep pumping it up and down again. As I said, with brine you need a certain period just to get the soil frozen. With nitrogen it goes very much quicker. The strength of frozen soil, that's something of a study in itself. Basically, if you want to know more about that, there's only 1 or 2 laboratoria in the whole of Europe that have any understanding of frozen soil and can test frozen soil. And you should also take into account that once the soil is frozen, you will have some expansion. Well, that won't be a problem in most of the project that we're going to do. But after the soil gets, after you stop the freezing, it will also reduce in volume. And that's something that you should always consider. As I said, nitrogen is a very fast method, but expensive. The properties of frozen soils, well, there are a lot of examples like this in literature that you can find. You should always consider this as, well, maybe upper or lower limits. You should never take this number for granted. What kind of applications do we have? Well, we can use the freezing method to make vertical shafts. making retaining and cut-off walls. We don't do that a lot, but we could use it in that way. Maybe the last one on this list is the one we're using the most in the Netherlands, is to make cross-sections between bored tunnels. You see here some examples from the surface view. One of the large vertical walls that have been created using this technique was for the subway tunnel in Rotterdam that had to be crossed. Of course, it was very hard to, it wasn't almost impossible to do it with any other kind of technique. So therefore this wall of frozen soil was created. For this technique we also made some holes through the tunnel, the existing tunnel itself, just to reach the soil beneath the tunnel. And to be able to install the pipes there, the tubes there to freeze the ground. This is a picture from a cross-section between two bored tunnels. And if we have a look at a more recent picture, this is from the Rotterdam Seban tunnel. You see all the freezing around the hole that was made. And well, the tubes were simply installed by drilling from one tunnel to the other tunnel, freeze the whole lot, and then dig the soil in between out of the opening that was made. Well, and finally, to leave you with maybe a comforting thought. Geotechnical engineering is based on two simple laws of nature. If you understand Newton's second law about gravity, and you understand it fully, and you understand the law of Archimedes about buoyancy, well, then you know basically all you need to know for being a geotechnical engineer. However, geotechnical engineering isn't that simple because we can't look into the ground. This man is doing his best, but even then it's not possible to see even more than a few centimeters below surface level. And what we cannot see, we cannot check, we cannot monitor it completely. So we always need to make our calculations, our engineering robust, simply to limit the risks that we're taking. And then, of course, if you start your career within a few years, you will probably know that you know everything. And then, well, you make some kind of mistake and you will realize that you don't know anything at all. And, well, after 30 years, trust me, it's complicated. Thank you.